electromagnetic force, we will have a lot of forces which we will try to have, like number one, normal force or contact force. Number two, we will have string force or tensile force. And number three, here we will have spring force, which we will now discuss about. Basically three kind of forces, and we will have another force that is called as weight of a body. Now we will analyze all these kinds of forces in a very simpler way. Let us have number one, normal force or contact force. This force arises when a body is in contact with another body, or a body is in contact with the ground, a ground is contact with a stake. Any kind of contact between any two kind of bodies, a force arises known as contact force or normal force, and generally I will have this as NF, normal force. So to make things simpler, I use normal force as NF. So here number one, I will write NF is always perpendicular to the normal force is always perpendicular to the contact surface. Example, suppose this is a ground, a body is in contact, normal force will be always be perpendicular to the contact surface. This is the surface, normal force will be always perpendicular to the surface. So here I say normal force is N. Or an example I can have, here the normal force is always perpendicular, always perpendicular. There are two contact surfaces, there are two contacts, so two normal forces will be there. So let us say this is N1 and let us say this is N2. Number two, if perpendicular to the contact surface cannot be drawn, then normal force is always perpendicular to the surface of the body. That means, for an example, I say this ladder or a stick is making two contacts. So for this contact, as discussed earlier, here the normal force will be in this direction. Let it be N1, perpendicular. In this case, normal force perpendicular to the contact surface cannot be drawn. So here normal force will be perpendicular to the surface of the body in this way. This is number two, where perpendicular to the contact surface cannot be drawn, then normal force is always perpendicular to the surface of the body, as discussed now. This is the case where normal force is, this is the surface of the body, normal force is perpendicular to the surface of the body, as discussed. If any of the 2 points discussed above can't be drawn, then normal force is resolved along two components. Like Example, in this case a block is resting in an haphazard kind of cave or something like that. Here at point A and at point B, normal force is not perpendicular to the contact surface. Normal force cannot be drawn perpendicular to the surface of the body. So in this case, normal force is resolved along two components. That is, one is along NAX, one is along NAY. Here also NBY, here it is NBX, and you can write NA is nothing but NAX square plus NAY square, and NB is nothing but equals to NBX square plus NBY square. It is immaterial in which direction you draw NAX and NAY, because ultimately NA and NB is nothing but NX square plus NA square root over. NB is nothing but NBX square plus NBY square root over. Now the string force or tensile force, when we talk about forces arising in this string, ordinarily we say tightness of rope or string felt in our hands is known as tensile force. That means in our childhood days we must have played tug of war. When we pull a string, the tightness of the rope felt in our string is known as tensile force. In tensile force, always pulls a body, never pushes a body. Now, when we talk in for JEE Mains in physics, we say idealized string. Idealized string means inextensible and massless string. That means there is no elasticity property in this string, and this string is massless. Now, when this string is massless, tension is assumed to be constant throughout the string. We say here tension means tensile force. I'll give an example. Suppose this is a string. It is pulled by an equal and opposite forces. Let us say F and F. And we say this is an idealized string. And if I ask you what will be the tension in this string, maximum of the students say tension in this string will be 0, but that's not correct. Tension in this string will be F only. How? Now you just divide the string at any point of the string. You just take any cross-sectional part. So this cross-sectional part, this is F, and as I said you earlier, tensile force always pulls this string. That is, for at this part the tensile force will be like this, T. You take this another part which was here, the tensile will be always pulls a string T. Now for this part of this string, since this string is massless, I can say T is equal to F. Here also I can say T is equal to F. So tensile force in this string in this case will be nothing but T is equal to F, and here tensile force is assumed to be constant throughout because here the string is massless. Now in this case, suppose a string is like this and pulled with a force F. Here tensile force in this string, obviously T will be equals to F only. So we must think that idealized situation for the case of JEE Mains, idealized situation means the string is inextensible, the string is massless, the tensile force in the string will be nothing but same throughout the string. Now what happens if the string is having certain mass? Let us have that kind of situation. Now when the string is having mass, let that mass be small m and length of the string is L. Example I take like this. Now earlier as discussed, if the string is massless, tension is same throughout. Now when the string is having certain mass, how the tension varies, let us calculate it. Let us calculate it some certain point at a distance x from this. Now for this x part of the string, as I say here, let the tension be like this. Let us calculate the mass of this part of the string. For L length, mass is m. For 1, it will be m by L. And I say it, repeat it once again. Here, the mass is distributed uniformly. So I put an asterisk and write mass of the string is distributed uniformly. Now for L length the mass is m, for 1 it will be m by L, for x part it will be m by L into x. Now for this part of the string, the weight acting, obviously the weight, I will extend another force, that is weight. Weight of any kind of an object is always acting vertically downwards. So for this part of the string, the weight will act downward, that will be nothing but m by L into x into g. So here tensile force T is equal to m by L into x into g. When x is 0, T is 0. When x is L, T will be nothing but equals to m into g. So here I can say the tensile force increases uniformly . The graph is certain like this. The tension is increasing in a linear wise with the increase in the position of x. That means when x is increases, the mass of the string is increasing. So the tensile force is increasing. At the topmost point, the tensile force will be maximum. That will be nothing but equal to the weight of the string, which I said over here. Now the same question where the string is having mass, length of the string is L. Instead of that string is there, I will hang a block. Now here again I want to find out the tensile force varying in the string. So T will be nothing but equals to capital Mg plus m by L into x into g. So when x is 0, T is only equal to the weight of the block, and when x is equal to L, T will be nothing but mg plus m small m into g. So in this case, the graph will be something like this. At x is equals to 0, T will be nothing but equals to mg. At x is equal to L, T will be nothing but equals to m plus m into g. This is the case when the mass of the string is distributed uniformly. If the mass of the string is not distributed uniformly, you need to find out the whole length of the by the principles of integration, where we will discuss about this in rotational mechanics or in center of mass chapter, where the mass is distributed non-uniformly in case of string, in case of lengthwise, in case of area wise, in case of volume wise. So the use of the string, basically for JEE Mains, we have the string is used in case of a pulleys. Now what is a pulley? Pulley is nothing but a groove like this, and this is an axle in which a pulley is fitted it. The best example you must have seen, when a bucket of water is being carried out from a well, the axle, the pulley is nothing but it can rotate freely with an axle mounted on it. And for an idealized situation, we say pulley is massless and frictionless. Frictionless means there is no friction between the string and the pulley. This kind of situations will have in rotational mechanics, where pulley is having certain mass and there is certain kind of friction between the pulley and the rope, which makes the pulley rotate. But here we are not taking in that case. Here the pulley, there is no friction between the pulley and the string is massless. When we talk about pulleys and the string, we say this is a pulley and this is the situation which we take. A block is hanging through a pulley, 3 kg block or 5 kg block. And now, since I have not spoken about Newton's second law of motion, so here I will not talk about how to find out the tensile forces or what are the acceleration of the bodies. Here I am only interested to make you know, since the pulley is massless and frictionless, here the string is massless, tension will be same throughout the string. So here the tension will be T like this. That means for this 3 kg block, tension will always try to pull 3 kg block. For this part of the pulley, tensile force will be this one, and similarly for this one, T will be like this, and for this one, the T will be like this. Tension always pulls the body. That means if I take the free body diagram of the pulley, the tensile force is like this. If I take 3 kg block, tensile force is like this. If I take 5 kg block, these are all the ways how to find out the tensile force acting on a block or acting on the string. Always I say, for the massless string, tensile force always pulls the body, and for a massless and an inextensible string, tension is same throughout the string. Now the third kind of force which will come along is spring force. The spring force says, spring is nothing but a metal coiled in various ways like this. This is a spring where a metallic wire is being coiled into various ways, or in many ways. It's said to be spring. Now what this spring has? The spring has got its natural length, which is said to be L naught. L naught is named to be natural length. Now, I connect this spring to one end of a wall. So obviously this has got its natural length. Now I try to extend this spring by certain amount. Like this. With a certain amount of force F. And the final length is L, I take. Now when I extend this spring to a certain length L, the atoms and molecules constituting this spring are in a vibrational state. Now if I ask question to the spring will say, if I am able to bring back this part of the spring to its original, that means the spring will say that I am in a vibrational state because my this part of the spring has been extended. That means if I am able to bring back this part of this spring, then I will be at its natural length. Now the spring force, the spring will apply a force when I am trying to pull this spring with an horizontal force F as shown. The spring will try to, and if I remove this F, the spring will try to bring back this part of the spring. That means this part of the spring means, I say this part of the spring is nothing but L minus L naught. And I say L minus L naught is nothing but X, which I say displacement of the spring. Now here I say X is equals to L minus L naught, that means final length of spring minus natural length of spring. Now if the spring is able to bring back this part of the spring, then the atoms and the molecules constituting this spring will be in a natural state. So here I say Fs is spring force, is directly proportional to minus X. Why minus X? Because here the displacement is positive, but the spring force always try to oppose this displacement. So I put a negative sign. So here minus negative sign only implies that spring force is opposite to the displacement of the spring. So when I remove this proportionality sign, I get Fs is nothing but minus Kx. So obviously this K is known as or spring constant. Now what this K defines? Here K defines the stiffness of spring or how stiffer the spring is. That means if K is more, the particular spring will be more stiffer. More stiffer means more amount of force has to be applied to displace this spring by a certain amount of displacement. And remember, this Fs is equal to minus Kx is defined as Hooke's law and is valid for very small displacements. Now we have already discussed when the spring is extended, the same Hooke's law will be, that means this is a natural state. I again define this. This is natural state. This is compressed state. This is again elongated state. So in all these three cases, Fs equals to minus k into x is to be applied, provided the displacement of this spring is very, very small. Now let us discuss when springs are in series. Now why I am discussing about springs in series, I will discuss about springs in parallel. I will try to have an equivalent spring constant. That means suppose this is a spring, these are two springs connected to a block of mass m, k1, k2. I just want to have an equivalent spring. Which I can substitute from these two springs to an equivalent spring. So I am applying a force F. Now when I am applying a force F, the same force is being applied on this spring, the same force is being applied on this spring. The total extension of this, or the total displacement of this block x will be nothing but equals to x1 plus x2. The net displacement of the block will be equal to summation of displacement of spring 1 plus displacement of spring 2. Now since the forces applied on this, and I am making this block move very slowly, so acceleration of the block has to be 0. The same force is being applied on this k2, the same force is being applied on this k1. You can have like this, on this m, same force F, on this spring k2, the same force F, on this spring same force F. So all the forces acting on this, both these springs are same. So I can say F by, instead of x I write k equivalent, this I will write F by k1, this I write F by k2. So all this F cancels. So I can write 1 by k equivalent is equal to 1 by k1 plus 1 by k2. This is springs in series. Number 2 will have when springs are in parallel. The case is like this. In this case, the two springs K1 and K2 are in parallel. I want to connect this with an equivalent spring constant. Now here, displacement of this block is equal to displacement of this spring is equals to displacement of this. You can say here, if I make this block move towards right, spring 2 is extended towards right. So spring force on 2 will be towards left. I repeat once again, when this block is displaced towards right, spring 2 is extended towards right. So spring force on 2 will be towards left. Same thing, when this block is displaced towards right, spring 1 is compressed. When this spring 1 is compressed, spring force on due to 1 will be towards left hand side. So the net force acting on this block will be summation of this force plus summation of this force. Here also same thing, when I make this block move, spring forces acting on this block will be in this direction. So the net force will be nothing but equals to, I can write F1 plus F2. F will be nothing but K equivalent into X. Here I write K1 into X plus K2 into X. So all this X cancels out. So here K equivalent becomes K1 plus K2. This is springs in parallel. Let us have a very simple problem related to these all springs. Now, these are all identical springs. Spring A, spring B, spring C. A, B, C are identical. Now, what happens? The block of mass M is compressed towards spring C by displacement x. Find net force acting on the block. Now ABC are identical. Block of mass M is compressed towards C in this way, and this is 90 degree given, towards C by displacement x. Find net force acting on the block. Now, when block is compressed towards C by x, spring force due to C will be Kx in this direction, and I am not mentioning here minus because minus shows the direction of force is opposite to that displacement, and here I have through vectors I have shown the force is opposite to the displacement x. Now, when this block is compressed towards C by x, so obviously when block is compressed towards C by x, horizontal displacement, that means this is x, horizontal displacement will be x cos 45. Vertical displacement will be x sin 45. That means this is x by root 2, this is also x by root 2. That means when the horizontal displacement is x by root 2, so obviously spring force, the spring B is extended horizontally by displacement x by root 2. So obviously spring force will be kx by root 2. Now when this block when the block is compressed towards C by x, the vertical displacement is x by root 2. That means spring A is extended by x by root 2. The spring force on A will be nothing but it will be like this, kx by root 2. Now there are three forces, kx, kx by root 2, kx by root 2. So since this is 45, so obviously this will be 45. So I can write here net force acting on block is kx by root 2 whole square plus kx by root 2 whole square whole root over plus kx, because the net force due to kx by root 2 and kx by root 2 will be along kx. So this total will be nothing but kx plus kx, which is nothing but 2kx. So the net force acting on block will be nothing but 2k into x. Now next is weight. Weight of a body always acts downwards. So I write weight of a body always acts downwards. Now these are all the kind of forces that we will encounter in Newton's laws of motion. When we discuss about JEE Mains, are the contact forces or normal forces as discussed, string forces as discussed, pulleys we had when we go to the Newton's laws of motion defining, and we had spring force and we had weight. So I extend this: forces are balanced. I make this Newton's first law of motion, that a body continues to be in a state of rest or a state of motion until and unless an external force acts on it to make the body to change from state of rest to state of motion, or state of motion to state of rest, or state of motion to a different state of motion with direction changing in case of uniform circular motion or in case of non-uniform circular motion. As I discussed, what is the definition of force? Force is nothing but a push or pull which tries to change the state of rest. Now, when we talk about state of rest or a state of motion, here I will go with another, then I will come down to forces are balanced. When we talk about state of rest or state of motion, a new quantity comes into existence called inertia. Inertia ordinarily, or if you ask what is inertia, the quantity of matter contained in a body is defined as inertia, but we say the mass. The more the, and what is mass? Mass is nothing but the material with which a body is composed of. If you say what is the mass of the body, I can say this mass of the body is nothing but a plastic material of this pen. If I take this pen to moon, the material, the plastic material will not become iron or something like that. So mass never changes. Weight changes depending on the value of g. So in inertia, in case of linear motion, we will say linear dynamics, and we say rotational inertia or moment of inertia when we talk about rotational dynamics. So in any case of dynamics, we will have inertia emphasized on it. That is, in linear dynamics we have inertia, in rotational dynamics we will have rotational inertia or moment of inertia. These two properties define whether how much amount of force or how much amount of torque. In case of rotational dynamics, we will have, here we have force and here we will have torque. When we will discuss about rotational mechanics, we will have this quantity torque coming into existence. So when we talk about inertia, linear dynamics, we will have force, how much amount of force has to be applied to make a body state of rest to state of motion. It depends on what is the inertia of the body, depends on what is the mass of the body. More the mass, more the inertia, more amount of force has to be there. So the definition of force makes us come to Newton's first law of motion, that every body continues to be in a state of rest or a state of motion until and unless an external force is applied to make the body change from state of rest to state of motion, or state of motion to state of rest, or state of motion to a different state of motion with direction changing. Now we will have forces are balanced. Body at rest or body is at uniform motion. Uniform motion means moving with constant velocity. Now when we say forces are balanced, summation of all the forces must be equals to 0. This is called forces are balanced. Either the body is at rest or body is at uniform motion, moving with constant velocity. And now I will try to say something about velocity now. Now when we talk about velocity, from the first instance we know velocity is a vector quantity. Vector quantity means it should have magnitude as well as it should have direction. So I will write magnitude is speed plus direction. Now what happens when any of the quantities changes? I will try to discuss about it now. Now number one, when speed changes, direction remains same. This kind of motion is known as rectilinear accelerated motion. That means we can say accelerated motion in one dimension. Accelerated motion in one dimension, that we have studied in kinematics. That means when a speed of a body changes from 5 meter per second square to 5 meter per second to 10 meter per second in 1 second, obviously the speed is changing. We can find out the acceleration from that. Now when speed changes, direction remains same, rectilinear accelerated motion. When speed changes or when speed remains same, direction changes. We have this kind of motion as uniform circular motion. And third, when speed and direction both changes, we have this kind of non-uniform circular motion. So I say when speed changes, direction remains same, rectilinear accelerated motion in one dimension, or I can write here translatory motion. And when speed remains same, direction changes, that kind of phenomenon is defined as uniform circular motion. Third thing, when speed and direction both changes, we say this is non-uniform circular motion. So here we have that kind of definition of velocity. As I discussed, forces are balanced, bodies are at rest, or body has to be at uniform motion. Uniform motion means velocity has to be same. When velocity is same, neither of both the quantities changes. Both the quantities have to be constant. If any of the quantities changes, then velocity has to change. So velocity is a vector quantity which has its own magnitude defined as speed and direction. Any one of the quantities changes, velocity has to change. If velocity remains same, both the quantities has to remain same.